All right, now we're going to talk a little more about those tree diagrams I referred to earlier. Right. Having the sample space for an experiment is super helpful when it comes time to calculate probabilities. Okay. So we can't always easily list them, but or think about what they would be, but tree diagrams and tables can sometimes help us organize our thoughts. So a tree diagram is a diagram consisting of branches corresponding to the outcomes of two or more probability experiments that are done in sequence. So when you construct a tree diagram, you use branches emanating from a single point to show the outcomes for the first experiment, and then you show the outcomes for the second experiment, and then show the outcomes for the third experiment, and so on. So I sort of was doing that like back in here when I was trying to ponder something like this. This would be the concept of the tree for that would have been that there's 5 possibilities for the first task, which is picking a letter for the first spot, but then after that there'd be 4 branches off of each of those letters, and then after that there'd be 3 branches off of each of the letters, and then after that just 2, because in that case each letter could only be used once. So tree diagrams can sometimes be helpful to just ponder what's going on in a problem, and it can help you get your sample space and the total number of possible outcomes. Okay, so here we got a situation that asks us to do a tree diagram to find the sample space for the sexes of 3 children in a family, and then compute the probability for various events they ask us about. So we're going to assume that being a boy or girl is equally likely, and this was 3 children, right, in a family. So we're thinking about that the first child could have been a boy or a girl. All right, now we're going to go and have branches emanating from each of those with boy or girl. Okay, for the second child. And then for the third child, be the same thing. We could get a boy or a girl for the third child, so we'll have branches boy or girl off each of those. Okay, third child. Okay, so those are like the 4 tasks: the first child, then the second child, then the third child. And so the tree can help us come up with a list of possible outcomes. So they could all be boys. See how that's what I would get if I followed this path, right? But it could be boy. Let me do a different color. It could be boy, and then girl, and then boy, right? Down here could be a different boy, then girl, then boy. But if I did use my tree diagram, that would help me come up with a complete list in a nice systematic order. So it could be boy, boy, girl, then boy, girl, boy, and then boy, girl, girl, if I followed this path, and so on. So I'm going to go follow the paths. Okay, and I like to try to line my outcomes up with my tree. So I'm kind of following along here, getting my girl, boy, girl, and then my girl, girl, boy, and then finally my girl, girl, girl. So there's the 8 possible outcomes. So there's 8 possible outcomes here. And the tree diagram helps you to get the list of those in a nice systematic order. Okay, so then we can use it to answer these questions. Suppose the family has 3 kids. If I wanted the probability they have at least 1 boy and 1 girl, at least 1 boy and 1 girl. At least 1 boy and 1 girl. So then it has to have both a G and a B in it. So it seems like the only thing it wouldn't be is not all boys or all girls. So there's 8 possible outcomes So those two, it couldn't be. So the probability that they have at least one boy and girl would be 3/4. Okay. On this one, let me add a word in here. If a family has 3 children, find the probability that they have, let's put in here, exactly. Let's be a little more precise. Exactly 2 boys. Okay. So then I would look up here, and because I have the list of possible outcomes, then I can just come up here and say, okay, exactly 2 boys. Okay, there's 2 B's, there's 2 B's, here's 2 B's, just those 3. So the only ones that I found that had 2 boys in it would be these. Those 3 outcomes out of the 8 possible outcomes. So the tree diagram helps you to get your sample space. And then if you have that sample space, the number of outcomes in that sample space, that 8 possible outcomes turns out to be the denominator. But what's really useful is actually having all the possible outcomes sitting there in front of you. Okay? All right, now this question is a different situation. We're going to flip a coin, and then we're going to roll a die. All right, so we're going to flip a coin first. So flipping a coin, tossing a coin. And then we're going to roll a die next. Okay, so when we flip the coin, it could be either heads or tails. Then we're going to roll a die. So we'd have 6 possibilities. If we're talking about just a normal die. Okay, and so my sample space would look like heads followed by a 1, heads followed by a 2, and so on. And then I'm going to write it over here, tails followed by a 1, a 2, a 3, a 4, a 5, or a 6. So 12 possible outcomes on that. Okay. Now the question goes on to say, find the probability of getting heads on the coin and an even number on the die. So both of those have to happen, heads and an even number. So that would be that, or that. Now, and or in a math class is pretty precise. If they use the word and, it means they both have to happen at the same time. You have to have heads and also an even number. So there'd be 3 outcomes. Okay, so the probability of heads and even number would equal 3 of the outcomes out of the 12 possible outcomes, and then you would just simplify that and get 1/4. Okay. Now, sometimes instead of doing a tree, we create like a table of all the outcomes that we then utilize. For instance, for the deck of cards, this picture that you see right here is just a normal deck of cards here. Okay, so you'll actually receive a picture that's a deck of cards like that. Okay, so if you're trying to do probabilities related to selecting certain cards from a deck of cards, having the deck of cards in front of you would sure be nice. So with a normal deck of cards, there's 4 suits. Okay, that's the hearts, diamonds, spades, and clubs. So that's these. These are your possible suits. Okay. And then each card, an ace, 2, all the way up to 10, jack, queen, and king, you have that in each suit. So there's 13 cards for each suit, which gives you the 52 total cards. And then the jack, queen, and king part, these guys here at the end, sometimes you get questions that talk about face cards. So in a real deck of cards, the jack, the queen, and the king actually have faces on them. So they're your face cards. All right, so here's some questions that are related to that table, but having the sample space just makes it very easy to do. So a card is going to be drawn from an ordinary deck. We're going to use the sample space above to find the probability of getting a jack. So there's 52 cards total, 52 cards. Right? So out of those 52 cards, there are 4 jacks, and we can simplify that to be 1 out of 13. All right, what's the probability I'm going to get a 6 of clubs? Well, here's the 6 of clubs. There's only one of them out of the 52, so it'd be 1 over 52. Okay, what's the probability of getting a 3 or a diamond? All right, let me erase what I have here so that I can, hey, I said to erase. All right, there we go. So I can show you the idea there. So if I wanted the probability of getting a 3 or a diamond, you could be a 3, you could be a diamond, or both. You got to be a little careful. So here's the 3s, here's the diamonds, but you don't double count this guy is the only problem. So there are 4 3s. So think of it like that. There are 4 3s and then 12 other diamonds that you haven't already counted. You counted this one already, okay, out of the 52 cards. So if it's an or like that, I could do the 4 3s plus the 12 other diamonds, which would be 16 out of 52. And that would simplify to be 4 goes in there 4 times, 4 goes in there 13, 4 13s. Okay. Now, you could also do this. You could also say 4 3s plus 13 diamonds, but then subtract off the one card that is the 3 of diamonds because you already counted him once as part of the 4, so you don't want to count him a second time there. So you have to take away 1 because you've double counted him. Some people approach it like that to get there for 4 out of 13. Okay, so those are the 2 ways to think about it. But if it said and a club, then it would be being a face card and also a club at the same time. Then I'm going to come in, so I'm going to do this one in blue. Face card and a club. These are the only face cards that are also clubs at the same time. So that's 3 out of the 52 cards. Okay. And you'd be done. So the hardest one here might be the C. And the thing you got to be careful with on ORs is not to double count. So the 3 of diamonds is both a 3 and also a diamond, so you can't count it twice, or you shouldn't count it twice. Okay. All right, now let's try one more common one. So let's suppose we're rolling 2 dice, or rolling 1 dice and then rolling it again. You can either think of it as 2 dice in your hand that you're tossing, or you rolled 1 and then you rolled a second one. And what you're seeing in this picture are all the possibilities about what those 2 dice could look like. So it's like for the first dice, you could have rolled 1 through 6, and then the second one could be 1 through 6, and then you just created this table. So it's almost like a 1 from here and a 1 from here is a 1 1. Okay? All right, 1 from here and a 2 from there would make it a 2 1. A 1 with a 3, a 1 with a 4, and so on. So those are all the possible outcomes, and what we see is that there's 36 possible outcomes. And we want to consider this one as potentially different than that one when we're counting up outcomes that fit certain events. All right, so you'll see what I'm talking about in a minute. So let me clean this up so we have full use of it. And let's just use it to answer some questions. What if we wanted to know what's the probability that we would roll the 2 die and get the sum to turn out to be 8? Okay, so I'm noticing 2 and 6 would be 8, 3 and 5, 4 and 4, 5 and 3, and 6 and 2. So there's 5 outcomes that add up to be 8 out of the 36 outcomes, and that would not simplify. Okay. Now, this one is asking us for the probability that we'd get doubles. Okay, so doubles would be same thing on both die. So here's the ones that are doubles. So there's 6 possibilities out of the 36. So we have a 1 out of 6 chance. Okay, so the probability of getting doubles is 1/6. All right, and then this question was asking, what's the probability that we'd wind up with a sum that is less than 5? Okay, so less than 5. I don't have, let me change colors on one of these. Let me change this guy. Let's change it to a bright orange, no, blue. Okay. All right, so sum less than 5. So less than 5, can't be 5. So here's 4, 4, 4, 3, 3, and then 1. 1, 2, 3, 4, 5, 6. So that's 6 possibilities out of 36. Or again, 1/6 would be the probability of getting a sum less than 5. So having a tree diagram that helps you to determine the sample space like we were doing here, so that you've got your sample space to refer to, or having a table like the deck of cards or the dice, both of those are ways of actually having your sample space, getting your sample space, and then that makes probability just a matter of counting stuff up. Makes it a whole lot easier.